So, what I have is the following. We have region, it turns out that region 2 or case 2 is the case of constant acceleration. We are going to measure this or quantify this acceleration purely via Newtonian arguments. Okay. Case 1, 3, 5 are my 0 acceleration or 0 net force, okay, and my case 4 is my constant deceleration. Okay. Okay. So, let us try to find all these regions of constant acceleration and constant deceleration, right. So, let us look at the region of constant acceleration and try to find how much time is taken by the inner nanotube to spend in this region, which is case 2, region of constant acceleration. So, in this case we set up our Newtonian equation, that is the via Newton's second law, m times d2z dt2 is equal to the force which is work done, negative of work done by d, or this is going to be minus ECC star, right. So, this is for region number 2, and now so we just plug in ECC star. Notice that the inner tube, so we need to integrate this equation twice to find out z as a function of t, and to do that we also need the initial condition. Note, we assume that in case 2 the particle or the inner nanotube starts with a 0 velocity, and let us integrate once to see what happens. So, integrate and use the fact that dz dt at t equal to 0 is 0. Integrate once and see that I get dz dt is equal to let me use the notation mod w, so that to avoid minus or plus signs. So, I am going to use the positive value here. So, w, right. So, this is a case of constant, hold on, let us look at the figure. So, minus w is negative or w is positive, right. So, we can peacefully use w to be a positive function, right. So, this is our w being positive, right. So, w is positive. So, I get that w by m d times t, right. So, that is the integration once, and further we integrate once more, and also use the position coordinate. Note that z at t equal to 0 is at a position coordinate. Notice that the boundary point of case 2 is at, so the case 2 will be, so this is the region of constant deceleration. So, we want to find out at the what is the value of the position between the boundary point 2 and 3, right. So, that will be given by this particular value L1 minus L2, or I see that z at t equal to 0 is L1 minus L2, and suppose the extrusion distance was d. So, we will get minus d. So, d is my extrusion distance. Okay. So, d is my extrusion distance, and what we see is that z is after integrating L1 minus L2 minus d plus w t square by 2 m d, right, W t square by 2 m d, and we want to see what is the value of this, what is the time taken by this oscillator, this inner nanotube to reach to region 3. So, time taken by the inner nanotube to reach region 3. Region 3 is when it has travelled a distance z is equal to L 1 minus L 2, right. So, we will take so this is at z is equal to L 1 minus L 2. So, we have to reach region 3 from region 2, then the center of the nanotube must have travelled a distance of L 1 minus L 2, right. Again from our, this is directly coming from our description of the cases. So, the cutoff point is L 1 minus L 2 going from case 2 to case 3. So, we plug that value of z and find out how much time is taken by the oscillator to stay in region 2, right. So, when we use z equal to, so use z equal to L 1 minus L 2, and from here I see that my time taken by the oscillator to stay in region 2 is coming out to be d times square root of 2 m by w. Let me call this as T 1, right. Similarly, I can find out in the region of no acceleration, in the region of 0 acceleration or region 3, in 0 acceleration region, which is our case 3, in 0 acceleration region which is our case 3, I see that my inner nanotube experiences no force. My inner nanotube experiences no force, because then it is going to travel with a constant velocity, and the constant velocity is given by plugging the value of T 1 in our previous results. So, experiences no force, it travels, it implies the nanotube travels from one cutoff point from z is equal to L 1 minus L 2 to the other cutoff point which is L 2 minus L 1. From one cutoff to the other cutoff is marking the region which is denoted by 3 with constant speed v given by which is given by the value of dz dt evaluated at t equal to T 1, right. So, dz dt that we found at t equal to T 1, right, and once we evaluate this I get the value 2 w by m, okay. Or my time spent to travel for the inner tube to travel in region 3 will be the total distance which is 2 L 2 minus L 1, right. So, point 1 to point 2 divided by the total divided by the velocity which is 2 w by m, and I see that I get a time point equal to 2 times L 2 minus L 1 times square root m by 2 w, right. Okay. So, finally, we also have the region of constant deceleration. In region of constant deceleration, well, we are completely modeling a system with 0 friction. So, the region of constant deceleration will be symmetric to the region of constant acceleration. Or students who do not believe this should directly find the time taken in this constant deceleration region similar to our similar to our analysis for constant acceleration case. So, in case of constant deceleration the time taken by the system will be again the time taken to spend in this region will be again T 1. This is via via symmetry arguments of the system. Okay. So, that is the result in short. So, now let us add up the total time taken by the system. So, what is the total time taken? The total time taken for one oscillation will be the time taken in the region of constant deceleration, right. So, that is in case 2 plus the time taken in case 4, which is via symmetry the same time, plus the time taken in case 3, which is the region of constant speed times 2, because the motion gets repeated after going from one end to the other. So, now we have that the total period of oscillation, or it implies the period of oscillation becomes 2 times 2 T1 plus T2, okay, 2 times 2 T1 plus T2, and this is also equal to 4 T1 plus 2 T2, and we can plug in all the values of T1 and T2 we have found, and we see that my period of oscillation will be T, which is 2 times 2 T1 plus T2, which is also equal to after plugging in the values of T1 and T2 will be equal to 4 D times square root 2 m by W, right. So, plus 4 times L2 minus L1 times square root m by 2 W, or I can club these two expressions. I see that my T comes out to be 4 times L2 minus L1 plus 2 D times square root of m by 2 W, right. So, that is my period T of oscillations, and in this case let me finally write down what is the oscillatory frequency. The oscillatory frequency will be given by f, which is also equal to 1 by T, will be 1 by 4 L2 minus L1 plus 2 D times square root of 2 W by m, right. Okay. Where my work done W is minus ECC, the cylinder interaction star D. Okay. So, this is my period of oscillation, which has now been found completely through the Newtonian mechanics. Now, notice that if my nanorods are almost similar in length, if my L1 is equal to L2 and the extrusion distance is minimal or D goes to 0, I see that my frequency goes to infinity, which means that small extrusion equal length nanorods frequency is almost immeasurable because it goes to infinity. So, this is just an observation. So, notice this observation, if we see that f goes to infinity when L1 is equal to L2 and D goes to 0, right, or this is the case of faster oscillations with lower amplitude, right. So, in the limit of 0 amplitude we expect that these oscillations are almost unreliably small to be measured. So, what I just said is that in this particular case, when the frequency goes to infinity, this is not a case of practical interest because these frequencies are almost immeasurable. Okay. So, 0, this is the case of 0 amplitude limit, zero amplitude limit is of no practical interest, because they cannot be measured without errors. Okay. So that is just one assumption. Okay. So let us now look at the same model of this oscillatory motion of these nanotubes via our Hamilton's equation or the Hamiltonian formulation. So now let us look at the variational approach. So let us try to answer question 3 using our variational approach. Okay. So that is via my Hamilton's principle. Okay. So now to write down my Hamiltonian, we have to look at what is my kinetic energy and what is my potential energy of the problem. So my kinetic energy of the problem is given by K is half m z dot square, right, and my potential energy of the problem is given by V, which is E c c star times. So, I am now going to write down the potential energy of all the 5 cases that I have discussed in the earlier discussion in the form of a single expression using my Heaviside function. So, V is E c c star z plus L 1 L z plus L plus times H of z plus L plus minus z plus L minus times times z of L z plus L minus H of z plus L minus minus z minus L minus H of z minus L minus, right. So, 1 2 3 plus z minus L plus of H of z minus L plus, and that is my potential, where my L minus and my L plus are going to be, well, we need to write down what is L minus and L plus. L minus is L 2 minus L 1 and L plus is L 2 plus L 1. Okay. Okay. So this is the potential energy completely written in a single expression using my Heaviside function. So, these are my Heaviside functions, okay, and with the usual definition. Okay. So, then we set up the Lagrangian, of the system, Lagrangian of the system. So, L is equal to K minus V, and then we set up the action integral, which is f of z of t. My action integral is integral K minus V dt, right. So, that is my action integral, and my Hamilton's principle says that the optimal solution to the action integral will be given by the principle of least action or the extremal to this action integral, right. So, by Hamilton's principle, I have the path of the tube, z of t is the extremal of the action, right. So, the path of the tube is the extremal of the action. Okay. So, then next, so we have to extremize the action integral, and we look at now the Hamilton's let us begin with our Euler-Lagrange equation, but even before that, notice that my Lagrangian, the Lagrangian is independent of the independent variable t, which means that we can very well use our Beltrami identity to reduce our Euler Lagrange, right. So, notice, so this is all from here. Note that my Lagrangian L is independent of the independent variable t, or from here if I use my Beltrami identity, I see that I am going to use the following. So, z dot partial L partial z dot minus L is equal to a constant, right. So, using Beltrami identity I get the following, and so this particular del L del z dot, that is completely a contribution coming from the kinetic energy, will give me m z dot square minus L is a constant, or my L is, so this, note that this quantity is 2 times the kinetic energy, right, via a definition, and L is kinetic energy minus the potential energy. Okay, so, minus the potential energy which is P, that is how, and then we rearrange this relation, we get that. So, 2 times kinetic energy minus kinetic energy plus potential energy is a constant, or I get that K E plus P E, right. Let me denote it by K plus V, this is also equal to a constant, or what I am getting is the Beltrami identity is telling me again the net energy is conserved in the system. Okay, so, then, so which means that the total energy is conserved. Okay, so total energy is conserved. So, I can also find this constant of on my right hand side of this relation. So, if I take my initial work W, take my initial work done to be W, my initial work done to be W, which is eventually minus E C C star times D, depends on how much is the extrusion length, right. So, if I take my initial work done W, then work done to extrude the inner tube by a distance. So, this is my E C C star times D, right, and my initial, take my initial kinetic energy to be 0, right, my initial kinetic energy to be 0, then the above, using this my above constant, this constant comes out to be W plus 2 L1 E C C star, right. Why this second term? Because of the potential of the system when it is not accelerating, because at in my case 3, that is the work done by the system. So, this quantity is the additional work done by the system in extruding out from the equilibrium position, right. So, this is the additional work done. Note that when we have 2 nanotubes, right. So, let me draw this figure here of the inner and the outer. So, we first extrude by a distance d, and also before even extruding by a distance d, it also has to be extruded by a distance 2 L1, which is the length of the inner nanotube. So, that is the additional work done because of this following diagram. Okay, so, my constant is the following which I have written. So, now from this relation I see that my K, my kinetic energy is equal to W plus 2 L1 E C C star minus V, or I can write down by plugging in the expression for V, I can see that this is also equal to minus E C C star times D minus 2 L1 plus Z plus. So, I am just plugging in the value of V, times the Heaviside function z plus L plus minus z plus L minus times the Heaviside function z plus L minus, right, minus z minus L minus times h of z minus L minus, right. So, d minus 2 L 1 plus this. So, 1 2 3 we have 1 2 3 terms, and then there is a fourth term also, plus z minus L plus times h of z minus L plus, right. So, these are my four terms, and from here I can see that this kinetic energy is also equal to m z dot square by 2, right. Or from this whole giant relation, I see that my z dot is equal to. So, let me denote this giant of an expression by small k as a function of z, right. So, from here I see that z dot or the velocity is 2 times k of z, the giant expression, divided by the mass of the nanotube m, and of course, this is my equation of motion. I can integrate it once and find out the time period of oscillation, but that is going to be very cumbersome. Instead, we look at the time period in a different way. Notice that from A, so I am not going to integrate A and find out the respective times of the motion of this particle, but instead I am going to directly I can definitely integrate A to find time period. What I can't do is to find the position as a function of time, because of the complexity of the square root function. So, I am going to integrate A to find the period of oscillation. When I integrate, I see that my half the period of oscillation is going to be given the integral of the arc length s by v. So, this is my v, right, and now I am going to. So, my limits are minus of L minus d to L minus plus d, right, and then this is also equal to integral of the same limits minus of L minus d to L minus plus d times dz divided by z dot, and then of course, this is going to be divided into 3 different integrals. This is also equal to integral of minus L minus d minus L minus d to minus L minus of dz by z dot plus integral from minus L minus to L minus of dz by z dot plus integral of L minus to L minus plus d of dz by z dot. So, these are the 3 different integrals that are being broken because of the use of Heaviside function. So, within these 3 integrals I have constant I have continuous description of z dot, or so z dot is continuous. Okay. So, these are my break points which are underlined, where my z dot loses the continuity of its continuity. Okay. Okay. So, then it turns out that this. So, let me specifically write down my function k z in these 3 limits of integration are as follows. So, this is minus E c c star times d plus L minus plus z. This is when minus this minus L minus d to z from minus L minus, and then the second region is E c c star times d. This is from minus L minus to z from L minus, and finally, minus E C C star of d plus L minus z, and where z is from L minus to L minus plus d, right. So, I have this following values of the function in these 3 regions, and then I plug it into all these 3 integrals, and let me write down the final answer after integration. I see that after integration I get the following: the half the time period is going to come out to be negative minus m by 2 E C C star times, of course, in the first 3 regions I am going to get minus L minus minus d to minus L minus of d z divided by square root d plus L minus plus z. In the second I have minus L minus to plus L minus, this is d z by square root d, and plus the last integral is minus L minus to L minus plus d d z by square root of d plus L minus minus z. Okay. So, when I complete the integral, I am going to get that this is also equal to 2 times square root of m by 2 w, where my w is E C C star times d with a minus sign times 2 d plus L 2 minus L 1, or I see that my t turns out to be 4 times this quantity, which is the same period that we have obtained, same period via as obtained via the Newtonian mechanics, okay, via the Newtonian mechanics. Okay. So, that completes my description in the Hamiltonian description of these nanorod oscillators, and I hope that the students have learnt in this course, starting from the basic theory of calculus of variations to how to apply this theory in optimal control problems, and finally, how to look at the motion of carbon nanorods in various situations. So, I hope the students are going to have learnt quite a few tricks to solve the problems involving calculus of variations with specific applications in optimal control and nanomechanics. So, thank you very much for listening, and thanks a lot.